Imagine a world without mobile phones or laptops. That's what my introductory sentence would have said if I was presenting this only 5 years ago. Imagine a world without high-tech, shiny, scratch-resistant touchscreen smartphones and durable, modern, super lightweight portable laptops. Technology is changing and developing indefinitely, and things we use daily are becoming more and more high-tech and intelligent. It is happening so fast in today's world because we have more efficient technology to work with as well. The technology of all our appliances would be impossible without modern polymer science. So let's start with some definitions. Monomers are small units which repeat and link together to make larger molecules called polymers. The process of connecting monomers together is known as polymerization. Here's an example of small repeating units of propene converting into its polymer polypropene, which is used in packaging and textiles. Polypropene is an example of a chain growth polymer, which are also known as addition polymers. Addition polymerization is the type of polymerization in which alkene monomers are added to the reactive end of a growing chain. The end of the chain may be a radical, anion, or a cation, making it reactive. Polymers can come naturally or be made synthetically in the lab. Chemists specializing in modern polymer science use natural building blocks to build synthetic polymers, and on the other hand, you have molecular biologists who use synthetic ways to modify naturally occurring biopolymers. There's an undefined line between the two, but we don't have to worry about that because this presentation will only cover synthetic polymers. One contribution polymers have made to the modern world of high technology is in liquid crystal polymers, PLC. Research in liquid crystals began in 1888 when an Austrian botanist, Friedrich Reinitzer, observed that a material known as cholesterol benzoate had two distinct melting points. He increased the temperature of the solid sample and watched the crystal turn into a hazy liquid. As he increased the temperature, the material changed again into a clear, transparent liquid. Liquid crystals are special in their properties and uses, and research into this field has developed new applications such as display screens, and liquid crystals will continue to play an important role in modern technology. PLCs are a class of materials that mix the properties of polymers and liquid crystals. These hybrids show the same mesophases characteristics of many ordinary liquid crystals, yet they keep many of the useful and versatile properties of polymers. For normally flexible polymers to display liquid crystal characteristics, rod-like or disc-like elements called mesogens must be placed into their chains. The placement of mesogens is important in determining the type of PLC that will be formed. Main chain polymer liquid crystals are formed when the mesogens become part of the main chain of the polymer. Side chain polymer liquid crystals are formed when the mesogens are connected as side chains to the polymer by a sort of flexible bridge. Main chain polymer liquid crystals are formed when rigid elements are incorporated into the backbone of the flexible polymer. These stiff regions along the chain allow the polymer to act similar to ordinary liquid crystals and thus display liquid crystal characteristics. There are two types of MCPLCs, depending on the way in which the stiff regions are formed.
The first type contains stiff rod-like monomers, which are usually made up of aromatic rings. In the second type of MCPLC, the mesogen is directly incorporated into the polymer chain. The mesogenic units comprise of two or more aromatic rings which provide the necessary restriction or movement that allow the polymer to display liquid crystal properties. The immobility results from restrictions on rotation caused by steric hindrance and resonance. This group is different from the first as the mesogens are separated or decoupled by a spacer. Decoupling of the mesogens provides for independent movement of the molecules, which allows for proper alignment. Notice that in the example structure, the flexible spacer, which are made of the methylene groups, and the stiff mesogens, the aromatic rings and double bonds.
It's not always easy to make PLCs that show mesogenic behavior over temperature ranges which are convenient to work with. In fact, a lot of the time the temperature of the liquid crystalline behavior is actually above the point where the polymer begins to decompose. So how can we avoid this problem?
Before moving on to the solutions, remember that at low temperatures, all polymers are hot solids. They are glassy. As the temperature increases, with more energy being put into the polymer, parts of the polymer chain begin to move together. The increased mobility of the material allows it to be compressed or expanded, so it behaves like a rubber. The point at which a polymer turns from a glass to a rubber is called the glass transition temperature, which is abbreviated to Tg. Heating the polymer further will give the polymer chains free translational motion. The material will melt and behave as a liquid. Polymers don't convert into gases, as they are such large molecules it would take too much energy. As mentioned before, the polymer would decompose instead.
The polymer's melting point can be lowered by arranging the monomers in the chain so that the molecules are put together in random orientation. For example, head to tail, head to head, tail to head, tail to head, and so on. Like atactic polymers, where the methyl groups are randomly oriented on both sides of the polymer chain. This minimizes interactions between the successive chains and allows for lower melting temperature. Copolymerization is another way of decreasing the temperature to a useful range. If a random copolymer can be created, the regularity of the chains will be reduced greatly. Reducing the symmetry will help to minimize interactions between the chains, which will consequently lower polymer melting temperature. The following picture shows how the irregularity of the polymer substituents can lead to decreased interactions. Lastly, defects can be introduced into the chain structure, which will decrease the melting point of the polymer as well. This method creates 120-degree kinks in the chain, which will disrupt the ability for neighboring polymers to line up properly. However, this method is not very efficient because this also decreases the effective persistence length, so too many kinks can actually destroy any liquid crystal behavior. Now let's put MCPLCs aside and move on to side chain polymer liquid crystals. Side chain polymer liquid crystals are formed when mesogenic units are attached to the polymer as side chains. These PLCs have three major structural components: the backbone, the spacer, and the mesogen. The versatility of SCPLCs arises because these structures can be varied in a number of ways. Now I have something in my room. I have these fairy lights which kind of look like SCPLCs. They're right here, so this is sort of like the backbone, and then you've got the spacer and the mesogen.
Other PLC types: polymer dispersed liquid crystals, polymer stabilized liquid crystals, pneumatic PSLCs, cholesteric PSLCs, lytropic LCs, and ferroelectric LCs. Cholesteric PSLCs are particularly interesting because they are used in a new high-tech application that I would like to introduce to you. Taiwan's Industrial Technology Research Institute, which I will refer to as ITRI, has come up with a highly innovative and award-winning flexible display screen, which they named FlexUPD, after starting research and development in this field in 2006, which was inspired by Popia spring roll skin, which are made kind of like crepes. Being flexible is seen as the up-and-coming trend in electronics. According to Dr. Jiang Chen, General Director of ITRI's Display Technology Center, the key to this award-winning FlexUPD technology is its ultra-thin and transparent soft plastic substrate. Once the transistors are layered on the plastic substrate and enclosed, it can be cut from the glass stage to make ultra-thin and rollable display that is only 0.01 centimeters thick. The secret of success is instantaneous removal through the use of a non-stick debonding layer material specially developed by ITRI, which allows for smooth removal of the plastic substrate from the glass stage. It is like a layer of non-stick material between a crepe and the pan. This new technology is cheap and easy to use and will help panel display manufacturers transfer their advantage in glass manufacturing processes over to flexible display production. To conclude, I would like to emphasize once again that polymer science has made an enormous contribution to the modern world of high technology and will continue to do so. Many big companies such as Sony, Nokia, and Samsung have already shown a great interest in flexible display technology, and there are some interesting concepts out there which may revolutionize old computer and electronic device designs with thanks to polymer science. The future holds endless possibilities once this technology is perfected, cheap and simple to use. Think of rollable mobile phones, rollable solar panels, interactive consumer products, and flexible laptops without hinges.